the universe undoubtedly extended, connecting perpetually outward. Top-notch in length after this period, it persevered to develop, albeit at a more sluggish pace, ultimately transforming into the universe we observe today. This is the inflationary hypothesis of the early Big Bang, the most obvious and widely accepted theory of how the universe began. However, some physicists argue that this theory does not conclusively explain the creation of our universe. They suggest that the universe existed before the Big Bang, stretching endlessly into the past as well as the future. While the universe is expanding today, they propose that it was contracting in its early stages. In this view, the Big Bang was not a bang, but rather a bounce. A moment when the contracting universe reversed direction and began expanding again. According to this theory, the universe could continue cycling indefinitely, its progress interrupted by periodic collapses in the far future, followed by new bounces. Some physicists even propose that this cycle might be infinite. This perspective challenges the standard cosmological view, which posits that all matter originated from a singular Big Bang. This notion is problematic because it's difficult to explain how something could emerge from nothing. Adding to the debate, the James Webb Space Telescope has made startling discoveries that challenge the idea of the Big Bang as the universe's beginning. These findings raise the question: if the Big Bang wasn't the start, then what was? Did the universe ultimately begin with a redirection or something else entirely? The concept of the universe having a beginning, or a night with no yesterday, dates back to Georges Lemaitre in 1927. However, proving that the universe had a definitive creation event remains elusive. The timeline of cosmic history barely aligns with the hot Big Bang phase that defined the early universe. Even so, a minority of scientists continue to argue that the Big Bang represents the true beginning of everything. By this definition, the Big Bang wasn't the birth of life as we know it today. In fact, there may be substantial evidence pointing to a more nuanced, non-singular origin of the universe, an idea we have barely explored. These conclusions remain tentative, primarily because no clear boundary or starting point is visible. The universe is often described as experiencing an inflationary period before the Big Bang. This inflationary phase is considered the precursor to what we now call the Big Bang. During this inflationary period, the universe was essentially empty, devoid of matter, photons, and debris. Instead, space itself was saturated with a tremendous amount of energy at every point. Over time, this energy evolved, interacting rapidly and systematically as the universe expanded. These changes resulted in mass increases and the creation of new scales, leading to what we now observe as the universe. This inflationary process remains difficult to fully comprehend. If you were living in an expanding universe during this period, you might observe neighboring regions where inflation seemed to end, causing distances between objects to increase. In short, understanding what happened closer to the beginning of the Big Bang becomes increasingly elusive as those regions fade from view. At the end of inflation, a small, dense region, perhaps no larger than a human-sized hamster ball but infinitely more powerful, underwent a dramatic transformation. The energy of this region was converted into matter and radiation. This transformation occurred rapidly, creating photons and other particles. Temperatures rose sharply, from just above absolute zero to around 20 Kelvin, in a fraction of a second due to the immense energy involved. This process, called reheating, marked the end of inflation and the beginning of the new Big Bang. As the universe continued expanding, changes occurred at near-light speed. All particles behaved like radiation, whether massless or massive, and the universe began to cool and slow its expansion. The initial moments of inflation gave way to a broader, more stable universe. Regions where inflation ended saw antimatter and radiation accumulate, growing larger over time. Meanwhile, areas where inflation continued remained distant and less accessible. In this cycle, the inflationary universe created the conditions for the Big Bang, leading to the formation of the universe as we know it today. The exact details of this process, however, remain a topic of ongoing scientific investigation and debate. Following the reheating phase, the universe transitioned into a state of rapid expansion and cooling. The immense energy generated during inflation began to convert into matter and radiation, marking the birth of particles such as quarks, electrons, and photons. As the universe expanded, the high temperatures allowed particles to collide frequently, forming protons and neutrons. Approximately 380,000 years later, the universe had cooled sufficiently for protons and electrons to combine, forming neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely for the first time. The result was the cosmic microwave background (CMB) radiation, a faint glow that serves as a snapshot of the universe at that moment. The CMB provides invaluable clues about the universe's structure and origins, supporting the Big Bang theory while leaving room for alternative models. Over millions of years, gravity began to play a dominant role. Small fluctuations in the density of matter, imprinted during inflation, grew into the large-scale structures we see today. These denser regions of gas collapsed under their own gravity to form the first stars and galaxies. The formation of stars ignited the process of nuclear fusion, producing heavier elements like helium, carbon, and oxygen, key ingredients for life as we know it. Over billions of years, stars exploded in supernovae, scattering these elements across space. This cosmic recycling enriched the universe, enabling the formation of planets and, eventually, the emergence of life. Today, the universe continues to expand, driven by the mysterious force known as dark energy. Observations show that this expansion is accelerating, leading to questions about the ultimate fate of the cosmos. Will the universe expand forever, growing colder and darker? Or could it one day reverse course, collapsing back into a singularity in a big crunch? Another possibility is the Big Rip, where the acceleration becomes so extreme that it tears apart galaxies, stars, planets, and even atoms. Alternatively, the universe could settle into a stable state, its expansion slowing to a halt. Each of these scenarios depends on the properties of dark energy, which remain one of the greatest mysteries in modern physics. In the search for answers, physicists are increasingly turning to new theories, such as string theory and quantum gravity, to explain the universe's origins and behavior. These frameworks attempt to unify the laws of physics, bridging the gap between general relativity and quantum mechanics. By doing so, they may provide deeper insights into the nature of space, time, and existence itself. Ultimately, the story of the universe is far from complete. From its enigmatic beginnings to its uncertain future, the cosmos continues to inspire awe and curiosity. As our understanding deepens, new questions emerge, driving humanity's quest to uncover the secrets of existence. Gradually, unlike the previously extending neighborhoods, the growing area becomes a customary relationship inside spacetime. In those districts where monster bangs occur, they will get as distant from one another's view as possible. In the standard inflationary picture, the expansion rate changes, and there may be a small chance that any universes with discrete, warm, large bangs will ever merge. The region we inhabit is rather fortunate, and progress seems to have reached an end for us. The influence normal for space itself gets converted into an influence-thick and almost uniform field of particles. The main imperfection arises from deviations in consistency due to quantum fluctuations that existed independently across the universe at a certain stage of its evolution. Initially, the high-quality energy quantum fluctuations balanced with overdense regions, while the low-energy fluctuations transformed into underdense regions. These fluctuations served as seeds for massive structures. We cannot observe those density variations as they existed during the universe's extreme early expansion. There are no visible markings accessible from that early stage. However, after further interactions, we can extrapolate backward to determine the initial density risks. Finding consistency aligns with the story of limitless improvement. The temperature fluctuations are imprinted in the cosmic microwave background (CMB), providing evidence of how the Big Bang began. Yet, notable irregularities remain. Most of the CMB and our advanced cosmological models are missing something, which can be summarized in 4 peculiarities. 1. Gigantic degrees. The universe isn't expanding as expected. Light from the CMB is being lensed through the Milky Way. Moreover, the CMB acts like a giant point of convergence, bending and altering the delicate return. The extent of this lensing is not always consistent with our state-of-the-art model, suggesting further investigation is needed. 2. CMB hemispheric temperature. The two hemispheres of the CMB sky show contrasting temperatures, challenging the assumption of uniformity in the early universe. 3. Hubble constant discrepancy. The value of the Hubble constant, describing how fast the universe is expanding, differs depending on whether it is measured using the cosmic microwave background or nearby stars. 4. Key missing elements. These anomalies suggest we are lacking something fundamental in our understanding of the universe. One proposed explanation stems from loop quantum cosmology, LQC, which originates from loop quantum gravity. According to LQC, there is a minimum size of space around. This framework implies that the classical Big Bang couldn't exist in such a universe. Instead, the universe may never have reached an infinitely dense state. In LQC, when the universe became very small, quantum corrections created a repulsive force, causing a bounce. This suggests that our universe might have originated from a prior universe that contracted and then expanded again, much like a phoenix rising from the ashes. While the idea of a big bounce isn't new, LQC provides a mathematical framework to support this cyclic concept. If this theory holds, the early universe might have exhibited gentle energy and density variations. These variations would align with the CMB, appearing as slight temperature fluctuations across the sky. Measurements of the energy spectrum further confirm the universe's origins, supporting the possibility of a bounce. Standard loop quantum cosmology offers a compelling and accessible alternative to the modern Big Bang model, potentially resolving some long-standing anomalies in cosmology and providing insights into the universe's origins. It also highlights the significance of preparing for unknown frontiers and maintaining a fair and noble perspective as we delve deeper into the universe's mysteries. As we explore the universe's origins and evolution, we uncover a rich tapestry of ideas and discoveries that challenge our understanding. From the early hypotheses of the primordial cosmic explosion to contemporary advancements in cosmology and quantum physics, the quest to unravel the universe's secrets has been marked by profound insights and enduring enigmas. The Big Bang theory, which emerged in the early 20th century, represents a pivotal moment in our comprehension of the universe's beginnings. It posits that the universe began as a singular point of infinite density and temperature, approximately 13.8 billion years ago. This initial state rapidly